I want to present a family of problems today that I guess the best way to describe them is that they are most at home in a polar kind of a coordinate system. And these stresses that are induced in these kinds of members, therefore, can often be divided up into a type of stress that would tend to maybe stretch the circumference of one of these round parts, and then another type of stress that would tend to push kind of radially outward or inward on the material of these round parts. And what I'm going to talk about today is going to culminate in the solution of this problem that you see here on the screen. But before I get to that, what I'd like to do first is kind of flip through some of the sections of our textbook that deal with these kinds of systems so that I can talk about them just a little bit. The first little section that we have here is the stresses in pressurized cylinders, is what the heading there is. And the first equations that you see are the most general equations that we have to deal with the stresses that get induced in what's called a thick-walled pressure vessel or cylinder. And these equations here, I guess the main thing I want to just say is most of these equations we're going to look at today, they are not that hard to understand. They are kind of plug and chug kind of equations. Yeah, you look at the figure, you figure out, okay, there's an internal pressure, an external pressure, an internal radius, an outside radius. Maybe the hardest thing to understand about an equation like this is this other variable of r. And that basically describes some arbitrary location within the material of the cylinder. So anyway, these are pretty easy equations to just use without having to worry too much about, for this class, we're not even going to worry that much where they came from. We're just going to say if you need to figure out these stresses, you can find them with these equations. The next set of equations down here changes one little thing, but it's a very common case that you see where you don't have any external pressure acting on one of these cylinders. So you only have the internal pressure. It's a common scenario that you might see in a lot of different cases, and it simplifies the equation a pretty good bit down to what you see here with 350. Okay? I guess, the next thing we'll look at here, actually this is a good thing to look at, is what exactly do these stress distributions look like in one of these thick-walled cylinders. What you see there is that you tend to, if you have positive internal pressure and zero external pressure, you tend to have tensile stresses the highest nearest the inside of this kind of a case, and then they taper off to being less toward the outside. You have a compressive stress that begins radially here on the inside, and that's compressive. It shows it negative down here, but then it tapers up to where you have zero stress on the outside if you have zero external pressure. So kind of give us a visual of exactly how those stresses might distribute in a thick-walled cylinder. All right. Another little piece to understand is that there's another stress that gets induced in these cylinders, and it is a longitudinal stress, is how they label it here. Another thing you might have seen that called in the past might be an axial stress, which would be a tendency to elongate the cylinder if it has internal pressure. So that's another equation that's given there for thick-walled cylinders. I've been using this phrase thick-walled cylinder a lot because some cylinders have a thin enough wall and where the stress distribution is relatively constant across the wall, and when that happens, what you have is that you can simplify these equations down, and where that sort of transition happens, they give a little guideline here that when you have about 1/10 or less of where the thickness of the wall is 1/10 or less of the radius, then you can transition into using one of these thin-walled pressure vessel kind of equations, and those are listed out there. All right, and for all three, both the tangential as well as the longitudinal. You kind of ignore the radial component whenever you're using these thin-walled assumptions. The next little bit that we're going to talk about is this idea of stresses that are induced in a ring or a disc that is rotating. And so I brought this in here so we can kind of think about what it is that causes the stresses in something that rotates like this. And matter of fact, people who have used, say, grinding wheels, this isn't a grinding wheel, but it's kind of like one, you may have even seen one of these discs fly apart when it's being used at really high speeds. The reason why that happens is that the disc is composed of all these little bits of material that each have mass. Well, those little bits of material also, when they're spinning, they also have a speed. And if you think about Newton's first law, objects tend to try to go in a straight line motion unless some kind of force acts upon it. Well, in order to make a little piece of material move in a curved path as opposed to moving in a straight line path, it actually has to have this force that acts on it to keep it moving in that curved path. Well, those sort of inertial forces, if you will, actually cause there to be stress induced in a disc like this. And again, we're not going to spend time right now deriving these equations, but there are a couple of equations that are given there in the text for the tangential stress and the radial stress, each of which are induced in one of these rotating discs when it's beginning to spin. What you see there with the rho is the density of the material that's spinning. Omega is the speed that it's spinning, and that's going to have to be in angular units of radians. I'll just make that note right now. We'll see that in an example here before too long. And then a lot of these other things, they're just the kind of dimensions of the disk. Again, we see this R without a subscript. That is the same kind of thing as we saw with a thick-walled pressure vessel, where it's a radius, or kind of a coordinate along the radius of the disk. It's sort of how far out are you away from the center is what that R without a subscript is, whereas Ri would be the radius to the innermost material of the disk. So if it's a solid disk that has no sort of inner edge, then Ri would be 0, and Ro is going to be the radius to the outside of the disk. So that's what is going on with those equations right there. The next thing that is covered here in the text is whenever you're putting parts together, one of the ways to, say, attach a part that has a hole in it onto a round piece is that you can make the hole in the part that you're installing on the round, a lot of times you call this one the hub and this one the shaft. One of the ways you can make sure that that piece will stay on there is you can machine the hole in the hub smaller than the size of the shaft, and then when you start pushing the shaft in there, the two parts will actually elastically, hopefully, deform. And as they begin to elastically deform, that creates a large amount of force and pressure between one part and the other. And that force and pressure, it actually creates this stuff, it's this parameter that we think of called the interface pressure between the two parts. That's sort of how much pressure exists from one part to the other. And that interface pressure creates force, and that kind of a normal force. That normal force then is useful to create kind of a frictional force against that part, and it won't want to come off or rotate relative to the two. So that there's a series of equations that we see here that allow us to relate here this P is this interface pressure, and the delta that they show, at least in this form of this equation, they're calling it a radial interference. It's essentially how much smaller is the radius of the part that you're putting on the shaft relative to the radius of the shaft. That's that radial interference value. And before I go too much further here, I want to show you that there is another section of this same textbook that talks about these press fits. And I'm going to show you this section because that equation that they show in that segment is a little bit different than this one. So if I flip over here, we see this form of this equation. And it's a little bit different. It's not much different, but it's a little bit different because all of these things are shown in terms of diameters. And they say down here, this delta is a diametral interference. And so these are very similar equations, and I want to just point out that the reason the delta here is a diametral interference as opposed to a radial interference is because I have diameter terms here and here. Those are actually the only ones where it's important that I use diameter in order to end up with a diametral interference, as opposed to the other form of the equation where I was coming up with a radial interference and I had to use a radius. Okay, I can go back there and show that real quick. Okay, so this right here, I've got this radius value right there. And when that is a radius, this is going to be a radius. You might see I also have radius values in these fractions, but I am free to use either radius values or diameter values in those two fractions right there, because if you think about it, to go from radius to diameter, you just have to multiply each term by 2. Well, if each term is also being squared, then that basically is like multiplying each term by 4. And I'll end up, I will have multiplied the entire numerator by 4 and the entire denominator by 4, which just cancels out. So in these two pieces, this right here and this right here, I am free to either use diameters or radius values. It doesn't really matter which I use as long as I'm consistent within each one of those fractions. Whereas over here, if I want a radial interference, that's got to be a radius. And if I want a diameter, then this has to be a diameter that you see here. All right, so that's where we're talking about press and shrink fits, and this is how we relate interface pressure to this radial interference. There is a slightly simpler form of this equation that we can use if we have where the hub and the shaft are both made out of the same material. This relationship here simplifies a pretty good bit. So I'm going to just mention that. The other thing that is going to be important for our problem that we're about to solve is that there are stresses that are going to be induced in both the inner member as well as the outer member whenever the two things are installed with each other. And the worst case for this kind of an interface will happen right at the interface for both members. So for the inner member, the worst case happens right at the point where it's contacting the hub, right? The shaft where it contacts the hub, the worst case is going to happen right there at the point of contact. And then for the hub as well, the worst case is going to happen on that inner face, right where the two parts contact each other. And just so we're comfortable with each of kind of all this terminology, what we're talking about here, this is a tangential stress that's induced on the inner member, right? That's what the T and the I stand for. This is saying that this is the kind of the worst case happening where our radius value is occurring at this capital R is talking about that interface radius between the two parts. And then it's giving this to us with this equation that has interface pressure, that radius at the interface between the two parts, and then the inner radius. I should mention what that is. This is assuming a case where you have a hollow shaft, and that's can be always used if you have a hollow shaft, or sometimes you might have a solid shaft where you don't have an inner size of this thing, and in those cases you plug in an Ri value of 0. Okay, so this takes care of the shaft part, the inner member. There's another form of this equation for the outer member, right? Right here, it's the tangential stress induced in the outer member, and this occurs at an interface, at the interface radius. So one of the things that you might notice here is that for the inner member, there's a negative value here. What this is saying is that there's going to be a compressive stress in that outermost ring of material on that inner member. And that kind of makes sense because you're putting this hub on there and it's going to try to crunch this thing down, which kind of makes it smaller in circumference. And as it gets smaller in circumference, you would imagine that would cause compressive stress in that inner member. Whereas this other one you see it does not have a negative sign there. That's because for the outer member, as it pushes over that inner member, it's trying to do the opposite. It's trying to get larger. It's like the circumference of any one little piece of material of that is trying to grow, and because it grows, it stretches, and that causes a tensile tangential stress in that outer member. Okay, so these are all of the equations that we're planning on using, and I just wanted to kind of run through these real quick. These equations, I guess, is the last thing I'll mention. These equations that occur for the stresses induced in these press fits, these are special cases of the thick-walled pressure vessel equations that I talked about just a couple of minutes ago. So that's what's going to, kind of come to bear on the example problem that we're about to work. Speaking of which, let's get into that right now. So for this example problem, what we have is we have a steel shaft that is being pressed into an aluminum hub. And so it says here this aluminum hub's press fit onto the steel shaft. The hub material can safely withstand shearing stresses of 20 ksi. Okay, now this is not necessarily the normal way that we think of strengths of materials. I'll talk about in just a few minutes here why I'm choosing to give you these strengths of these materials in terms of shearing stresses. Anyway, so let's just say that this is how we know. This is kind of a strength value, so to speak, of what these materials are, but it's given in terms of shearing stresses. And it says that the shaft material can safely withstand shearing stresses of 34 ksi. Okay. It says here there's a copper disc that's going to be installed on the hub with light torque in the nut. The copper of this material can safely withstand shearing stresses of 18 ksi. And what we're supposed to find are the maximum allowable radial interference between the shaft and the hub for part A. And for part B, we're supposed to figure out what's the maximum speed that this whole assembly can spin before the disc reaches unsafe shearing stress, that copper disc. All right, and you can probably tell I've got a MathCAD sheet down here that I'm going to use to compute all this stuff. I mentioned earlier that a lot of these problems tend to be kind of plug and chug. You tend to find all the parameters that you need and plug them into the equations, and because the equations are not necessarily difficult, but they can have a lot of terms in them, I figured MathCAD would be a good way to present that kind of material without having to get bogged down in the specifics of doing the calculations. So there is a big concept, though, that I want to touch on in kind of a general way for this problem that I'm going to kind of do in general first, and then I'm going to get into showing you how it pertains specifically to the stresses that are induced with this particular press fit. So this big idea is that whenever you have stresses acting in a little element of material, so I'm going to show here a little element of material. You can transform stresses and everything that are acting on that piece of material to the point where you come up with some principal stresses. All right, so we've been touching on that in this course for a while, but let's say that I wind up with a few principal stresses on here, and just for the sake of concept, I'm going to ask you to think of the lengths of each of these arrows as being sort of proportional to how much stress there is, and then kind of the direction also proportional to how much whether it's compressive or tensile stress. So let's say I've got a relatively large tensile stress there. Let's say that I've got a relatively small compressive stress happening on this face, and then we won't see it, but there's another one opposite on the other side. And then let's say I've got a kind of rather larger compressive stress happening on these faces right here. Okay, so let's say I've done all the work to figure out what my principal stresses are on this little element of material. Once I've done that, I can think of the total state of stress on this body as you can kind of think of it on a Mohr three-circle diagram, right? So let's say I draw this diagram such that I'm putting my shearing stress up here and my normal stress here. And we look at each of these, I tell you what, I'll call this one sigma 1. I'll call this one sigma 2. And I'll call this one sigma 3. Okay? And I'm going to plot each one of these values along these axes right here. So let's say sigma 1 would be relatively large over here. Okay? And then sigma 3 is relatively large over on this side of the axis. And then I've got sigma 2, which is also compressive, but it's relatively smaller. And the Mohr three-circle diagram would look something like this, between, and I should label these. Let me call this sigma 1, this one's sigma 3, and this one's sigma 2. So there would be a circle here that would kind of represent the kind of the plane between 2 and 3. There would be another circle here that would represent the plane between 1 and 2. And then there would be another circle here that would represent the plane right between 1 and 3. And if what we're trying to do is figure out the maximum shearing stress that occurs anywhere in this block of material, what you have to always do is make sure you look at whatever your largest stress is and whatever your smallest stress is, and you figure out what that distance is between those two, right? If you take half of that distance, what you end up with is the radius. I didn't really mean for it to necessarily land on that axis right there, but you end up with the radius of that outer circle. And you'll notice that if you find that radius, right, of that outer circle, then that radius, also that same radius, gives you whatever that maximum point is on your largest circle. And that point, whether you talk about the positive or the negative side of it, that point there is your maximum shear stress. And we're going to get much deeper into this. We're going to talk about this a little bit more in a lecture that's coming soon, where we deal with a criteria that's actually known as the maximum shear stress failure criteria. But for right now, just understand that what we've been given on this problem is that each of these materials, we're told how much shearing stress each of these materials can withstand. And there might be some work that we have to do to figure out what is the actual maximum shearing stress that is being experienced in each one of the parts, so that we can compare that against the shearing strength for each case. Okay? And so that's what we want to get into right now. Is let's look at part A right here. Okay, so part A, and specifically we're going to look at, I guess we'll start with the shaft, right? So there's a shaft on the inside. We could have, it's possible that the shaft could end up experiencing its sort of failure stress. It could reach its, was it given here? 34 KSI of shearing stress that it can withstand. It's possible that could happen first before the maximum stress is reached in the hub, or it could be reversed. The hub could reach its maximum stress, kind of its failure stress, so to speak, before the shaft. So we have to figure out both of them. Let's look at the shaft first. All right, so here's the shaft, right? And let's actually look at a little piece of material. We said a minute ago that for these press fits, we have to look at that interface location between the shaft and the hub, because that's going to be our worst case place of stress. And what I want to point out here is that basically, because of the press fit and the equation that we saw here in this material, right? This would be for the shaft. We have this tangential component of stress that's going to be compressive. That's what that negative sign is doing right there. Okay, and that's going to push in on this little piece of material like this. Meanwhile, there's also this interface pressure that happens between the hub and the shaft, and that interface pressure occurs all the way around the outside, right? I can draw them all on there, but you get the idea. So if that's the little element of material, let's actually kind of pull it out of there and draw that little element of material right here. Okay, that little element of material would look something like this. I'm going to go ahead and draw it in a 3D orientation. What we're saying there is that we have a tangential component of stress that occurs like this. Okay. And we have a radial component of stress that occurs, and it's basically just going to be that pressure, that interface pressure that occurs right there. And if we want to see how that sort of reacts on this infinitesimally small little element of material, it would just be another pressure of P down there. Okay. And then the third direction is one that we should think about. It's kind of this direction that goes this way, right? And I'm showing it there because it's important to always think about all three dimensions that you have possible on one of these little elements of material. But I'm going to point out that there's no stress along that axis because there's nothing that's actually trying to push lengthwise along this shaft. There's nothing that's trying to deform a little element of material in the shaft along that direction. Okay, well, if this is how this thing works, let me kind of scroll down a little bit. What would, if that's our little element of material, what would our Mohr three-circle diagram look like? Okay, you'll notice that I've got two components of compressive stress, and I also have no stress in the other direction. So what that means here is that on my my two axes, let's say this is my normal stress, this is my shearing stress for this little element of material. What I have is that I'm going to have one component here that's 0. That's that axis, and that's actually going to be my sigma 1, right? I also have these other two compressive components of stress. And at this point, I haven't done enough analysis to figure out which one of them is going to be larger, right? So let's actually take a second and look at this equation and see if, for our situation, for this little shaft, which is a solid shaft, right? A solid shaft, how does the interface pressure, at least in conceptual terms, how does it relate with the tangential component of stress? Okay, and so we'll go back into this material here, and you'll notice here that Ri, I mentioned this earlier, Ri is 0 because we have no hollow nature of our shaft. And so Ri is going to be 0 in each of these. R is just equal to R, capital R. And so this whole fraction over here is just equal to 1 for this equation right here, which means that my interface pressure is going to be equal to my tangential stress. Okay, so that actually makes this relatively easy for us to deal with here, because we'll say that we have 2 points right on top of each other over here, right? This point right here represents both my tangential stress as well as my pressure, right? And our circle is going to exist right there. And we'll only really see one circle because the other two circles are kind of infinitesimally small right here at these two equal stresses. And so if we think about this, the kind of the maximum shear stress that occurs in this case, right, to get to this point is the radius of this circle, and it's just going to be equal to half of the interface pressure. And really, technically, I should say that this P is not just P. This is, since P is always given as a positive number, this technically should be minus P over here, because I'm getting a compressive stress where my values of P are always going to be expressed in terms of a positive number, even though it is kind of by its nature compressive. So that's kind of a tricky thing there. Well, if that's minus P, right, that's shown over there, well then the height of this thing is really just P, right, over 2, which is just going to also be equal to sigma T over 2. That's what that little length is right there that gives me my maximum shearing strength, shearing stress. All right, well that's a value that would be appropriate to compare with the strength value that I am allowed to go up to for this material. And so that gives us enough information now to where we can get into MathCAD and we can actually solve for what that allowable interface pressure actually is. Okay, and you know, so what we'll do there is basically, you know, kind of for this first line, I'll tell you what, I'll put a label on here. We'll say if the shaft strength controls, all right, that actually, I know that's a bit of a brief description, but sometimes that's all it takes for us to kind of remember what we're doing with it. What we're saying with that now is that we can take this interface pressure P and divide it by 2, right? And then this is going to be equal to, all right, the strength value, right? Because the shearing strength value that was given for this shaft was 34 KSI. I have that listed up here as this allowable stress for the shaft is 34 KSI. Okay, so let me just put that in here as T. If you hit Control G, that gives you a Greek letter there. Allowable, and this is for the shaft. Okay, now I started putting this in with a Boolean equal sign, but it would actually be easy enough for me to, instead of writing this way, P is going to be equal to 2 times, right? This is the same thing, and if I do it this way, then I don't have to use a Boolean equal sign. I can use an assignment operator, and this will give me my pressure value. Okay, and if I kind of type in here KSI, that'll tell me what that value actually is, 68 KSI. And what this allows me to do now is to understand what my interface pressure is going to be between the hub and the shaft at the point, you know, at the amount of you know, interference that would cause the shaft to fail. Okay, so based on this, I should be able to take this interface pressure and go back into my equation that relates interface pressure to radial interference, and that way I can figure out what that radial interference is going to be. I want this delta, right? So let me put that in here. I'm going to put this delta with a subscript of shaft because this is the radial interference basically that the shaft side of it can tolerate. And I'm going to put that in with that interface pressure P times, so I'm going to kind of slightly manipulate this equation a little bit there. R is the interface radius at the location where the hub interfaces with the shaft. And so I don't have that, but I do have the diameter of the shaft, which is basically the same thing. It's just a diameter instead of a radius. So I'm going to put in here D shaft. And in order to get the radius, I'm going to put in D shaft over 2. Okay. And this is going to get multiplied by 1 over, okay, this is the elastic modulus of the outer member. And I kind of put these in here without talking about them a whole lot, but you'll notice here we have elastic constants for our members, the shaft, the hub, and the disc. If you're curious where those came from, there's a table in the back of Shigley. It's right here, table A5. And what you see there is that for all of these materials, we've got that elastic modulus as well as Poisson's ratio looked right up out of that table. Okay. Back to doing our relationship here between interface pressure and radial interference. Okay, so we have the elastic modulus of the shaft, is what I call that, E sub shaft. Okay, that's for the outer, excuse me. If I want this to match perfectly, I should do the outer member first. So this would be not for the shaft, for the hub. Okay, now I'm going to multiply that by this fraction right here. Now, this fraction, and then I'll go ahead and put in this other term before I get back to the fraction. The other term is the Poisson's ratio of the outer member, so that would be, okay, to get Greek, again, I can type the English equivalent and hit Control G. I'm going to get that for the hub. And here, I'm going to take the, it's more convenient for me to do these in terms of diameters instead of radiuses. And that's something I can totally do now because I'm going to do it consistently. So RO for the outer member. You might actually look down here if you want to make sure you know what that is. RO is the radius to the outer edge of the outer member. Okay, so I'm going to put in there, instead of RO, I'm going to put DO hub. Okay, and I'm going to square that. Okay, and then I'm going to add to it the diameter of the shaft, which is the interface diameter, and that'll be squared. This will be divided by DO hub squared minus D of the shaft squared. Okay. And so that takes care of all of that first part of this thing. I tell you what I'm going to do. A lot of times it's easier to do kind of a cut and paste. So to this I'm going to add, and what I'll do here is instead of retyping this whole thing out, let me change the things that need to be changed, right? So now I'm dealing with the inner member, which is the shaft. So I'm going to get the elastic modulus of the shaft. All right. And you'll see here I need the interface, right? So this is just going to be equal to D shaft. And here I've got the inner, right? And we talked about this a second ago. The R sub I is the inner radius of the inner member, which only exists if you have a hollow shaft that is being pressed onto. We have a solid shaft, so we're going to put in a 0 right there. Okay, now let me grab all that. And the only thing that changes in the denominator is that this is no longer a plus right here. This is a minus. All right. And then the only last thing I need to change here is that we need the Poisson's ratio for the inner member. And so I changed this subscript down here to shaft. Okay. And this should take care of everything that I needed to find that diametral, excuse me, not diametral, the radial interference between the two parts. Okay. If I want to see how this calculates, I can find D, hit Control G to make that Greek, type shaft, oops, and we'll see what's in there. All right, gives it to me in scientific notation, which is fine, or if you want to see it without the scientific notation, you might want to change it up a little bit. Like this. What it ends up telling me here is that the shaft, I like putting a border around for any of my results, but that for the shaft, it can tolerate up to 6, almost 7 thousandths of radial interference between these two parts. Okay? Now, you might have an intuition about this and kind of think to yourself, that seems like it might not be the shaft that controls how much this thing can tolerate in terms of its radial interference. So that's where we're going to go next with this is what if it isn't the shaft that controls this? What if instead we have something that is controlled by the strength of the hub? So we'll say if hub strength controls how much we can have. All right, this ends up being a little bit different, okay? So let's think about this in terms of the hub side. I drew this little sketch of what it looks like on the shaft side. And if I want to look at what it looks like on the hub side, I would need to do a little sketch of that, right? So I've got a little, here's what my hub would look like. And our worst case location for stress in the hub is again going to be right there at the interface location, right? And it's going to be experiencing this pressure, interface pressure, acting on that little element of material. But then it's also going to be experiencing a tangential component of stress. So here's our P, and then our tangential component of stress act on that little element of material. And so just like before, I'd like for us to think a little bit about what that element of material looks like in terms of 3D. That little element of material is going to have that tangential component of stress acting this way. It's going to have a pressure P, that's the interface pressure, acting this way, right? And just like before, there's nothing that's inducing a stress along the third axis, right? So again, we end up with no stress there. So what does that mean in terms of what the, okay, I'll make a little division here, but what does it mean in terms of how does the Mohr three-circle diagram look here? Okay, well, let's draw it, right? Here I've got the normal stress, here I've got shearing stress. And what we'll see here is that we do have three components here of principal stress. I've got one that's positive, sigma t. I didn't kind of go back and look at that, but if you look in here, we had this negative sign for the last one for the shaft. For this one we're about to work on, there is no negative sign. We have a tensile stress that's happening in the hub part of this. And so if I draw this, I end up with a sigma t as a tensile stress over here. I have a P, right? And again, to make this really technically correct, I would put minus P, just like I did before, because P is always a positive number, but I want to indicate it that that's a negative stress because it's a compressive stress. And then we have a third component of stress along this other axis where there's no stress, right? So there's zero. And so, tell you what, because I want to make this kind of look more clear, I'm going to make it look like this one's smaller. If I draw my Mohr three-circle diagram, it looks like this, right? And what I find there is that my maximum shearing stress, which again is the radius of this circle, is going to be based on half of the difference between this location and this location. If I figure out how far it is from sigma t over here to minus p, then that gives me what the that's what the total diameter is of the outermost circle of my Mohr three-circle diagram. The maximum shear stress is half of that diameter. It's this radius value. And so what we need to do here is, it's a little more tricky than the last time, because now P and sigma t are related to each other based on that equation that we have out of Shigley. But then they also both come into effect when we look at our failure criteria, or like what we need to compare to in terms of this maximum stress, right? We can go up to 20 ksi for the hub material. And so why don't I start there, and I put this in here and say my tau, to get that again, Control G, my allowable stress for the hub, right? We're going to say that this is going to be equal to sigma t, right? So like this. And I'm going to name this kind of a little bit differently. I'm going to call it sigma t. We're going to call this I. It's the inner surface of the outer member. So let me call it sigma ti for the hub, because by putting subscript of hub on there, that makes it obvious which one I'm talking about. Okay. If I take that and subtract from it a minus p, well, like this, and divide this by 2, right? That is my maximum shearing stress that occurs in this little element of material. You know, when it's divided by 2, it gives me that maximum shearing stress, and I'm setting it equal to my allowable shearing stress. So this is one of my equations, but you'll notice here I don't know sigma ti and I don't know p. So what I want to do here is come up with a second equation that allows me to relate those two, and that second equation comes from here. Okay. This is the tangential stress on the inner face of the outer member, right? So I'm going to use that same variable right there. We're going to say that it's going to be equal to, again using Boolean equal sign, P times, here these are again more convenient to use in terms of diameters instead of radius values, and because we have a complete fraction, it's okay for us to do that, right? But we end up with a little bit of a hang up, just a slight thing here that goes on with MathCAD that I still haven't been able to figure out. I've tried putting this equation, or this fraction in here just like it's shown, and it makes the solve block that I'm about to set up not work. And so what I figured out as a workaround for that is to basically split up this fraction to where I put part of it on one side and part of it on the other side. So I can put in here, for instance, DO hub, okay, squared, minus D shaft squared, and here I'm going to do the same thing but with plus. All right, and that basically gives me what it's saying there with that equation. In order to really make this a solve block, there's a couple things I need. I need an initial guess, okay, for this variable right here. So let me just call it 10 KSI. I don't know what they're going to be, but let me just call that 10 KSI. And I also need an initial guess for P. So let me call that also, I guess, 10 KSI. It doesn't really matter what I pick there because it's going to find what they really should be. If you've seen me work these before, I usually, if I'm using a variable as an initial guess, I always like to go in here and change the color so that it's a little reminder to me what I'm doing with those. So then I need a word given, and then down here I need to put in a matrix of solutions. Okay, and the two things that I'm trying to find there are P as well as sigma, okay, which I'll get that with this method, TI hub. All right, and I'll do find P, comma, oops, sigma TI hub. Okay, and then what I really want to know out of this is P. That's the interface pressure between these two parts. So I'm going to have it tell me what that's going to be here. And as I'm looking at this, I just now noticed that I've got a an error here. I should not have had a negative there. I should have had a positive. Okay, so let me fix that. That looks more like the answer I was expecting. Okay, so here, and put this again and see what that tangential stress is going to be in that case. Okay. Now, this wasn't actually what we were looking for, though. If you might remember, what we were looking for was what is our allowable radial interference between these parts. But you might remember that in our previous case, we took the interface pressure and we were able to convert that into a maximum radial interference using this equation right here. And again, because I like to make my efforts as efficient as possible, what I'm going to do is use this equation again, but modify it slightly. And I don't actually need to modify it much because I really just need to rename it. All right. Everything else is the same. We're still dealing with the same kind of type of interface pressure. It's a different value of interface pressure because now it's the amount that's controlled by the stress in the hub, but the relationship is still the same between interface pressure and radial interference. And so all I have to really do is rename this thing. Okay, and let me check on one other thing here real quick because I think there might have been another error. Yes, right here, this should not have been plus. Let me go ahead and show up here where this, right here, there's a negative sign right here, and I failed to get that in my first equation down here. So glad I noticed that too. Put in a negative sign here, and I'll put in a negative sign here. All right, and it changed those two answers slightly. I mentioned earlier it was about 6/1000ths of an inch. This one is a lot smaller. This one is only about a little bit more than 1,000th of an inch of radial interference that we can tolerate if it is the hub that controls what that value actually is. Okay, so we've got those set up now, and I believe that is what we were asked to find in our original problem. All right, the maximum allowable radial interference between the shaft and the hub. We're not quite there, I guess, because we have two different possibilities. Which one of them is it that actually controls what this radial interference can be? Well, think of it this way. If you have more radial interference, you end up with more stress. If you end up with more radial interference for the hub, you're going to end up with more stress than we assumed we could have for the hub. So it's going to be the smaller one that controls which of these it could be. Right? So if you want, you can put in another little line here that says that our allowable radial interference between these two things is going to be equal to the smaller, which is, you can get that by typing min, of what the two things are, right? The one for the shaft and the one for the hub. Okay, and then what we end up with there overall for our allowable radial interference is just going to be the smaller of those two. Okay, so that's part A. We just finished with part A of this problem. We know that we can go up to 0.00144 inches of radial interference before we overstress either the shaft or the hub. The next piece is we need to figure out what this maximum speed is that this assembly can be spun before the disc reaches unsafe shearing stress. Okay, And you might remember that section in the text that we looked at a second ago, right? These are the equations that would control what we're trying to work with there. And so we're going to grab these equations and try to implement them in MathCAD here. What's tricky is there are a couple of things in this equation where we're not quite sure what they need to be yet, right? One of them is pretty obvious. We don't know what this angular speed is going to be of these shafts. We also don't know how the stresses are going to relate to the strength of the material. You might remember that we can go up to a certain amount of shearing stress in the material before it fails. That's kind of like a strength. We don't know how these things are going to necessarily relate with those before we start working it out. And then we also don't know what the radius value is in the disk. Again, looking at a disk like this, how far out is our worst case stress going to occur? We don't know what that is before we start working with this. And because of all of these pieces of uncertainty, what I'm going to suggest is that we go in here and enter these as functions. Okay, kind of go on to my next page here. And I'm going to enter one as a function for the tangential stress. And I'm going to put this in terms of R and omega. Okay, I'm going to define this function in terms of R and omega. All right, other thing that's a little tricky here is that rho, I mentioned it earlier, but rho is a density of this material. We don't have the density of the material yet. I don't think that was one of the pieces of information that I grabbed when I was looking at these material properties. But the good news is that information is available in that table of material constants over here. You'll notice here that one of them is copper, and copper, it isn't actually given to us exactly as a density, but it's given to us as a unit weight, which is a force per volume instead of a mass per volume. And this actually brings up an interesting point that I'll go ahead and show you right here. The US system is kind of funky in a lot of ways, but you know, if I'm going to define this unit weight, which, you know, a lot of times the variable for that is gamma, okay, I can do that with this 0.322, okay, pounds force per cubic inch. Okay, I'm going to show you this. What would I have to do to turn that into a density? Well, I'd have to take that same value and divide by acceleration due to gravity. Okay, but with the US system, we have another unit for mass that is called pounds mass. In MathCAD, that's just plain lb. If I take that plain lb per cubic inch, notice what I end up with. It is just 0.322 pounds per cubic inch. Okay, so if I had wanted to, I could have gone in here and just immediately defined this density, rho, with 0.322 just plain pounds, lb, per cubic inch. And that would have been just a fine density for us to use. So, I don't know. There's a lot of things that make the US system kind of weird and sometimes not very convenient. This is one spot where it can be used for a little bit of convenience if you want to. So, all right, now we've got rho defined. So I can go down here again and just put in rho. Okay, like this. Here I'll just put in an omega squared. Whoops. I need to turn that into omega. I guess I should go back to my equation that I was about to use here. All right. I'm going to multiply this by a fraction here. This fraction is going to be 3 plus the Poisson's ratio for the disk, which I believe I called that nu sub disk. Down here I'm going to have 8. And I have another group of variables here. These radius values, I do need those as radius values. I can't convert them. I can't just use diameters instead. So what I'll do to get that is dO of the disk over 2 squared plus di of the disk over 2, and this is going to be squared. Right? To this I'm going to add, okay, again, I need to leave these as radius values here because I need r to stay as a radius, because that's what I'm doing this with respect to, is radius. So what I'll do is I'll take that di of the disk, okay, and I'll square it, and I'll multiply it by dO of the disk. And I meant to divide that other one by 2 before I squared it. So let me go back and fix that for this one here. Okay. And then all of that is going to be divided by that r squared. All right. Okay. Now I'm going to subtract another fraction. This fraction is going to be 1 plus 3 times nu of the disk over 3 plus nu of the disk. All of this times that r value again squared. Okay, now that gives me a function in terms of r and omega for my tangential stress that's going to be induced at any particular given radius, right? It's a function, so we can pick any radius within the disk at any speed that the disk might be rotating. The next equation is very similar, and again, I'm always one that likes to make my life easier if I can. Let's look at the things that change. First of all, I want to change the name. I'm going to go to a radial stress. Everything here at the beginning kind of stays the same, right? All this stays the same. This is the first place I see a change. I've got a negative number right here where I had a positive before. So I need to take this and get rid of that positive and put a negative, like that. All right, over here I see another change in that I don't have minus this fraction times r squared, I just have minus r squared. So I need to get rid of all of this, like that. Okay, and I believe that takes care of it. I will note, I guess I did reverse outer and inner, but those end up being the same, right? I've got inner and outer there. I've got outer and inner, but because they just add it, it's not a problem. Okay, so those are my two functions. And what I'm going to do next, because I don't necessarily know before I start this process where my worst case scenario is going to be for maximum shearing stress in this disk that's spinning, I can get some insight on that if I take these functions and I plot them for a particular value of omega. Okay, so let me do that. I'm going to put in an omega, I don't care what I call it, but let me say omega sub I, just as a kind of a test case. Let me just call it 1500 radians per second. Okay, just as a number to use. All right. The other thing I'm going to do here is I'm going to establish a range variable let me call it r sub r. This range variable is going to describe the range over which r can legitimately vary. So in other words, r has to start wherever the disk starts and has to end wherever the disk ends. So if we think about this, r should start where I have di for the disk over 2, right? The next value I'm going to use is actually that same thing again, di for the disk over 2, but add a little tiny bit. Okay, I'll add a little tiny bit onto that. Okay, and then the way these range variables work, you have to add on, or the last term that you put in your range variable after your dot dot, which you get with a semicolon, is the highest value that it's going to be. So do for the disk over 2 is the last variable or last value that I should have in this series that I'm establishing with this little range variable. And because these are kind of special variables here, I'm going to highlight them a little bit differently. Let me put those in this color here. These are sort of, you know, a range variable and then a test value for my speed. Put those in there like that. Now that I have those established, let me go ahead and plot these functions. To get a plot in here, I'm going to insert a graph, xy plot. Here I'm going to plot my range variable, but I want to do that not with the default units. I want to use inches instead of the default units. And over here, I'm going to plot sigma sub t against that range variable r sub r at my test speed, angular speed of omega I. Oh, like that. And I don't want that to come out in just its basic units, you know, its default units. I want to specify that I want it to come out in KSI. Okay? And here in the, for my other value, let me actually take this same thing again, because it's going to be the same, but I want to put in a second curve that is for my radial component of stress as opposed to my tangential component of stress. So this is referencing these two functions that I showed up here, and it's showing me what those functions look like as I plot them against radius. Okay. Try to make it a little bit smaller so we can see it a little bit easier. All right. Now, we have to kind of do a similar thing that we did for looking at stress in the hub and in the shaft. We need to look at this plot and figure out where's our worst case scenario for stress, okay, for part B. Now, let's think about our Mohr three-circle diagram, okay? As a matter of fact, let me start sketching it. So the Mohr three-circle diagram for this case would involve there being, these are both positive, right? This is our positive stress in the radial direction. This is our positive stress that we have in the tangential direction. We're going to have zero stress, the direction of the disk that's kind of along the axis of the disk. There's no reason why there would be stress in that direction. The only stresses we're going to have are radial and tangential acting in the disk. And so, and it looks like everywhere that we look, the radial stress, right? We look at the radial stress right here. It's always smaller than the tangential stress. So I can plot those kind of like this. Anywhere I look, I'm going to have a radial stress and a tangential stress. And that would set up a Mohr three-circle diagram that would look something like this. Which means that that outer circle again is going to control, this is 0 over here, that outer circle is going to control what the maximum shear stress is going to be. Right? This is normal stress, this is shear stress. Maximum shear stress occurs because of that outer circle. And so only thing I need to know here is what my tangential component of stress is to figure out what those, maximum stress values are going to be. Okay, and this actually holds even if you go all the way to one end or the other. We'll see here that the tangential stress goes to its max all the way here at the inner edge, where my radial stress goes to 0. Okay, and what this, Mohr three-circle diagram looks like at that limiting case is that I'm just going to have my sigma t here, where my other two stresses are both going to be clumped up here at 0. So 0 and sigma r, both at that location. My conclusion won't change. I'm still going to have my maximum shearing stress. It's still going to occur because of sigma t only, right? And it's going to be half of sigma t. Okay. Well, so what? What do we do with that? Well, it's actually not that hard to do something with it because I've already defined this function sigma t in terms of r and omega. All I need to do is solve this thing for an omega that's allowable, right? So let me do that this way. I'm going to define a variable right here that's omega allowable, right? Before we reach the shearing stress that this copper can withstand. Let me go ahead and just start here with, it doesn't really matter, let's just say 100 radians per second. Okay, as an initial guess. Then I type given. Set up a little solve block right here. Okay. And what I'm going to say here is that my allowable stress for the disk is going to be equal to my tangential stress. Okay. This is going to be at a radius value that is going to be the diameter, the inner diameter, right, of the disk over 2. Okay, that's because we notice that it's that inner radius where this worst case scenario occurs. So I'm taking this as the inner radius for those functions. And then I'm going to put in here this omega allowable. Right? All this divided by 2. Okay. And then what I'm going to do is have MathCAD solve, okay, to find that omega allowable. Like this. Right? And this is a value that's in radians per second. All right. If I want to change how this looks, I can just increase this exponential threshold and it'll give it to me as just more of a straight number without the scientific notation. All right. The other thing that you can do with MathCAD, it's not too tricky, is you can have it report what this value is instead of in radians per second. MathCAD does have a conversion from radians per second to RPM. So I can put in an RPM turns out that this is going to be able to spin pretty fast. 17,000 RPM is pretty fast angular speed for this, but that is how much speed it would take in order to take this up to the point where we have a shearing stress that would cause the copper to fail, according to the givens of the problem, right? This up here said it could withstand 18 KSI of shearing stress. Okay, so that's kind of interesting as an initial thing. If you want, you can actually go in here then and update this to something close to the 17, I believe it was 1789 or so radians per second that we 1789 or so. And this gives you what those stress curves would actually look like at the speed, kind of that limiting speed of its maximum speed it can go before reaching those shearing stresses. Okay. One last thing that I'm going to touch on here before we finish up, and it is this. Anytime you see a curve that ends up with a kind of a maximum value somewhere in the middle, that's always interesting to me. And so I'm going to actually go ahead and mention that we can figure out where this maximum occurs in this curve for the radial stress. Even though it doesn't matter to us for our question of how fast can we spin the disk, it might matter for some other reason. I don't know. And there's a couple ways to do that. One is in MathCAD there's a function you can use called trace. And this is kind of a quick and dirty way to do it. I can have it trace along this curve, right, and go, sometimes it looks a little odd when we do that, but as I trace along that curve, I don't know why it's having such a problem, but anyway, the point is, when we trace along this curve, it does have the ability to report back to us. Scroll a little bit here. It does have the ability to report what the values are that it traces to. Right? You see the values changing over here even though the picture is going all crazy. All right. So those are some interesting things that that we can get out of here, but we might want it to be more accurate than what we can get by just tracing along the curve, right? So we remember our calculus. Whenever we're trying to figure out where that location is along the curve, the slope of the line that's tangent to that curve at that location is going to be 0. And we know a function, this is a function right here that we've defined for that curve. And so one of the things we can do here is a combination of a solve block, right, on a derivative, right? So let's say this, we're taking this derivative of this function, right? And we're going to do this to find a particular r. Okay, so let's say r for sigma r max, something like this. Okay, and we're trying to figure out what that radius value is, where we have our maximum radial stress. And we'll just put in a number here. Doesn't matter a whole lot. We'll just say, let's assume it's going to be 1 inch for this solve block that we're about to do. Highlighting this region blue so that I know that's an initial guess. All right, I'm going to type the word given. And then I need to make sure that for this function right here, I'm using this same r variable, right? So I'm going to take that and copy it and put it right here, and also put it right here. We're going to solve this for where this speed is the maximum also. So I'm going to put in, instead of just omega, I'm going to put in this allowable speed. And this is all going to be set equal to 0. Okay, and then we're going to solve it for this same value, right? The radius where this maximum radial stress occurs. All right, so find and where this is going to occur in inches, 2.049 inches. Okay, does that look like that's a possibility? When we look at the 2.049, definitely looks like that's a possibility for where that could be on the chart. What might we want to know at that radius location? Well, we might want to know what this value is, right? So I might want to take this and say, tell me what that function is, right, at that radius location. And I might want to know what it is in KSI. 9.655. Right, let's see if that kind of makes sense over here. Right, looks like it could be. It's not too far off. All right, or I might want to know what is the tangential. Tell you what, I'll just copy this whole thing and change one thing. Right, if I change this to a t, then that'll tell me what that tangential stress is at that location. 20.864 gives me that stress somewhere in this range. Looks like that's also could be about right. So I hope this was useful, and if it was, then please subscribe, like, share, comment, all that good stuff, and I will catch you on the next video.